quality question here. So we've got an early morning drive. We've got n sets of traffic lights, and they're either red, amber, or green. I'm going to use R, A, and G to indicate that. And we never get consecutive lights the same color. So we can't have green and then another green and so on. The thing that makes this question tricky is that we are told an extra condition, there are at least two red lights. And that actually complicates things because if there was no restriction, it would actually be really simple. Well, I say simple, like if you understand arrangements and so on, it is relatively simple. I'll talk about that in a minute. But the fact that there's at least two red lights complicates things a little bit. And we're asked for a simplified expression in terms of n for the number of possible sequences. So honestly, I think a good way of going about this question is just to start with some small numbers and look at the options. So we can't just have two lights in total because you're not allowed to have red, red, but we have to have red, red as well. So the smallest number of lights, n is going to have to be greater or equal to 3. Okay, that's kind of the first thing. So let's look at 3 lights. Right, because we have to have at least 3 reds, then the first and the last one got to be red. So it's going to be R, G, R, and R, Y, R. There's going to be 2 possibilities here. Right, that doesn't give us a great deal of insight, but it's at least a starting point. Let's now look at n equals 4. I could put R and then G and then R and then G. That would be one option. But actually, if I start, like this is where I want to start kind of thinking about arrangements. So if I have R first and third, then actually, yeah, okay, we could have G and G, or we could have G and Y, or Y and G, or Y and Y. Actually, there's 2 options here, and there's 2 options here, and we multiply them. There's going to be 4 options. I'm actually going to cross that out. There's going to be 4 options when I have R first and R second. Then if we instead just move it and put our second and fourth, it's going to be exactly the same again. 2 options here, 2 options here. So I've got 4 and I've got 4. And I'm not allowed to have R's together. So the only other option is to have R there and R there. And then there's 2 options here. I could either have green or yellow. Sorry, am I using amber? I'm using yellow instead of amber. I don't know why I just got into that. Started it. Let's going to keep going with it. But now for this second one, if I choose green, I have to choose yellow or amber. So actually, it's 2 times 1. And overall, there's going to be 10 options. Right, now when I got to this point, I started thinking, okay, this is getting messy already. If I look at n equals 5, there's going to be loads more. There's going to be, potentially 3 reds when I have n equals 5, and when I go to n equals 10, like I could have 2 reds or 3 reds or 4 reds potentially. So I don't want to go down that route. So the question is, how can we do it a little bit simpler? And so at this point, I thought, can I get the result for 10, but using a different approach? Okay. Now, we've got this restriction of at least 2 red lights. So why don't I look at the case where I could have any number of red lights, including 0 or 1, and then subtract the number of red lights, subtract the number of sequences when I get 0 red lights or 1 red light. So new approach. Sequences with no restrictions minus sequences with no red lights minus sequences with 1 red light equals our answer. Okay, that we'll be left with all the sequences with 2 or more red lights. So this seemed like quite a nice little approach. Okay, so I'm just going to do it 4 lights to start with, but I'm just trying to explain where I'm coming from, how how you would know how to get the final answer. We're only dealing with 4. So let's look at no, and we're trying to get 10 as our final answer. So we can kind of check that it's working. This is a nice thing. It's kind of like do a little bit, get like an experimental result, create like a theory essentially, and then test that theory and justify it and so on. So no restrictions, right? This is what I said at the start, like about it being relatively easy if you have no restrictions, because we could have 3 options for the first one. It could be red, green, or yellow. And then whatever you have, you can't have it again. So now there's going to be 2 options. Okay, because if you have red, you're not allowed to have red here. But whatever you have here, you then can't have here. So there's going to be another 2 options. You could have the same as the starting one. There's no problem with that. And then finally, 2 here. So we get 24. It's 3 times 8, 24 options for the no restrictions. And in general, you could generalize that, and that would be like a simpler problem to this one. Okay, let's now look at when there's no red lights. Right, so I'm not allowed to pick red, so there's only going to be 2 options here, amber or green. But then I have to pick the other one. Okay, I'm not allowed a red, and then I've got to pick the other one, I've got to pick the other one. So there's 2 ways I could get this, no red lights. That's it. And now I'm going to look at 1 red light. Okay, so here, got to think a little bit more carefully. I could have the red light in different places and it would affect what is going on. So if I put the red light here, for example, then I'd have 2 options here and then 1 and 1. Okay, so I get 2. Right, let's look at what happens if I put the red lights here. Now I get 2 options here, but because I put the red light in between, there's again 2 options here, so it's not quite the same. 4. And the same will apply if I put the red light third. It's going to be 2 options and then, sorry, writing it below, aren't I? 2 options and then 1 option. It has to be the other one. If I have green here, then I have to have yellow here. I can't have red or green. And then, but here now I've got 2 options. So I'm again got 4. And then finally, but you can see some symmetry going on. The final one, having red here, is going to be the same as when I have red at the start. So there's going to be 2 options, but then 1 and then 1, 2. So overall, if I add these up, I've got 8, I've got 12. Okay, so we had 24 when there's no restrictions. We had 2 when there's no red lights. And now we've got 12 when there's 1 red light. So let's test this, see if we get our answer of 10. So 24 was no restrictions, minus the 2 for 0 red lights, minus 12 for 1 red light. And hey, we get 10. So we're working on our theory. It works. And now we just need to generalize. You could try out 5 lights. I think when I did it, actually, I didn't write down all the different ways of writing 5 lights, but I kind of applied my theory to 5 lights just to see if it works. So I'm gonna keep going, okay? Because I couldn't just go straight to the answer. I think it needs, I mean, if you can, fair play, but I think it needs like building up. That's often the way in maths. Like start with a simpler problem, build our way up to our general n lights. Okay, here goes. 5 lights. So no restrictions. All right, there's 3 ways, and then there's 2, and there's 2, 2, and 2. Okay. Now actually, I'm going to simultaneously do the general case because it will link in better. So for the general case, there's going to be 3 ways for the first one, for no restrictions. Then there's going to be 2 options and 2 options, okay, and we carry on to the very end. But because I've got But here I've got 3 times 2 to the 4. You can see that we times by 3 and then we times by 2 4 times, one less than the number we have. So it makes sense that here we can justify it, like, and in the actual problem you would be expected to justify it. But it's going to be 3 times 2 to the n minus 1. I feel like I'm doing a good job anyway of showing all my working. Okay, brilliant. It's like it's an exponential. Um, right, let's now look at 0 reds. Right, for 5, and then we'll generalize it. So there were 2 options. Oh, sorry, right below 2 and then 1. Okay, there's always going to be just 2 ways you can have it. Because you can either start with green and then you have to alternate, like you can't change it, or you start with amber, and then you have to alternate. So we're always going to get 2. Okay, I think doing it alongside is pretty good. Right, finally, we've got this situation where we're looking at 1 red light. Let's deal with it for the case of 5 and then generalize. Probably going to be the trickiest because, like you saw, there was some symmetry when we did it up here with these two being equal, but these two are not equal. So it's a bit more complex than the 0, and it's a bit more complex than the no restrictions. Okay, 1 red. Right, let's look at the situation where red is at the end. So I put red at the end, and then there's going to be 2 options here, and then it's just going to alternate. Okay, that's it. But then I'm going to get the same again here. There's going to be 2 options, and it's going to alternate. So I'm always going to get 4 here. In fact, 4 ways that I could have 4 ways if R is at the end. Okay, let's take a little look at if R is not at the end. Sorry, I'm having to move this down. Okay, it's going pretty well, I think. Right. So now I'm putting R somewhere else. And I'm doing it for, oh yeah, I forgot this. I'm doing it for 5, aren't I? Wait, I got a bit mixed up. So I actually just did the general case, but it was also true for 5. So I'm just going to copy and paste it down here. Okay, sorry. So this was I was just timesing 2 by 4 lots of 1. I'm not going to modify this now, but yeah, hope that makes sense. Right, then for red being here or here, I remember there's 5 of them now, sorry. Or here, it's very similar, but now I've got 2, but then it can be 2 here as well. And here I've got 2, and here I've got 2, then it's 2 here. So I'm going to get 4, I'm going to get 3 lots of 4. Or should I say 4 lots of 3? Because we get 4 for each one, and then there are 3 different places that I can put R. And that is going to help us out actually, because it's just the number of places that are not the end. This will allow me to generalize. So we get 4 for each um, each position of R. And how many positions of R are there going to be? There's going to be n minus 2 positions of R because it's just n, the number of lights, but not the end ones. And therefore, it's going to be 4 lots of n minus 2. So we're there actually. The overall answer is going to equal 3 times 2 to the n minus 1. That was when we had no restrictions, all the way back up here. Then I'm going to minus 2 from it for all the situations where we get 0 reds. And then I'm going to minus 4 for the times when we get 1 red light, but the red light is at the very end. And then I'm going to minus 4 lots of n minus 2 for those times when we get 1 red light, but the red light is not at the end. Whew. All right, just need to simplify it. We've done all the hard work, so it's going to be 3 times 2 to the n minus 1. I'm going to get minus 6 minus 4n plus 8, double negative here. So 3 times 2 to the n minus 1 minus 4n plus 2. All right, so I've taken quite a bit of time to explain this because it's unlikely you're going to write that straight down, to be fair. I've explained how I did it, just starting out. I think the 4 one is key, really. Seeing what the answer is and then like creating an idea and seeing that it works and understanding why it works. And then trying to generalize using n equals 5 to get an idea of what's going on. Okay, not just writing down all the possibilities because there were quite a lot at that point, but using it to facilitate the general case. Justifying the general case, okay, a few more words needed to explain this, but there's a lot of text here. Tough problem for sure, but it's a really good one. Okay, well done for watching all of this, and I hope it makes sense. Thanks.